What I want to do now is to move on to look at the third assumption we made of the classical linear regression model disturbances, and that is the assumption that these disturbances are statistically independent of one another. Now, there are a number of ways to write this, and what I want to do first of all is just to show you what those methods are. So this was the assumption that the covariance between the ith and the jth error term is 0. Another way to say that in the context of time series data would be to say that we assume that the covariance between ut and ut plus j is 0 for all values of j equals plus or minus 1, plus or minus 2, and so on and so on. Okay, so this is another way to write the assumption that the disturbance terms are statistically independent of one another. This assumption that we make is one, or we could say, of no serial correlation in the disturbances, or no autocorrelation in the disturbances. So what we're looking for here is to obtain a set of residuals from an estimated model with no patterns in them. We want the residuals from our estimated model to not contain any autocorrelation or to not be related to their previous values. Before we move on to look at how we test for this assumption and whether it's violated or not, we need to introduce a couple of new concepts. The first concept is the notion of the lagged value of a series. So suppose that we've got some series yt that takes the value 0.8 in September 89, 1.3 in October 1989, and so on. We could define the one-period lagged values of this series of y to be the values that y took in the immediately previous period. So for October 1989, the one-period lagged value of y would obviously be 0.8, because that's the value that y took in the immediately previous period. Similarly, if we wanted to, we could define a set of two-period lags. So for example, the two-period lag for y in November 1989 would be 0.8, because that's the value that y took 2 periods ago, and so on and so on. We could define as many lags as we wanted to. Another piece of terminology I want to introduce is that of what we call the first difference of y. The first difference of y is sometimes written delta yt, and delta yt is defined as delta yt equals yt minus yt minus 1. Okay, so this is sometimes called the first difference of y, or the change in y between time t minus 1 and time t. Obviously, we can construct a column of observations on the first difference in y simply by taking our observations on y and subtracting away from that our column of observations on the series yt minus 1. We could similarly, if we chose to, construct a column of second differences of y, and so on and so on. It's important to note that when we construct lagged values, or when we construct differences, we lose observations. So if we construct a column of one-period lags of y, we obviously lose the first observation. Because if our sample started in September 1989, we don't have an observation that preceded that to make the first lagged value of y, that is for yt minus 1. So in a spreadsheet, it would be as if when we construct the one-period lagged values of y, we shifted all of the column of observations down by one place in the spreadsheet. If we constructed a 10-period lagged value of y, we'd obviously lose the first 10 observations, and so on. Now, we'll need these pieces of new notation later on when we come to look at how we test for autocorrelation and how we fix any problem of autocorrelation that we have in our model. So once again, we can never observe the population disturbances, so our tests for autocorrelation are forced to focus upon the estimated residuals from the regression model. Now, in general, there are broadly 3 sets of patterns that we might see in a plot of residuals, and I'm going to go through those one at a time. So the first set of these plots is what we call positive autocorrelation. Now, there are 2 ways that we can construct plots of residuals. The first is to plot the residual at time t on the y-axis against the values that it took in the previous period on the x-axis. In the presence of positive autocorrelation, what does that mean? Well, positive autocorrelation means that on average, the residual at time t is positively related to its previous value. So if the residual at time t minus 1 is positive, on average the residual at time t will also be positive. If the residual at time t minus 1 is negative, on average the residual at time t will also be negative. So if we were to plot the residuals on the y-axis against their values in the previous period on the x-axis, in the presence of positive autocorrelation, the majority of the points would be in the top right-hand and bottom left-hand parts of that diagram. We could also plot the residuals over time. What would that look like for positive autocorrelation? Well, remembering what I said, that positive autocorrelation means if one residual is positive, the next one will be most of the time. If one residual is negative, the next one will be most of the time. Remembering that, then we can see that positive autocorrelation would indicate that there would be a cyclical pattern in the residuals if we plotted them over time. So positive autocorrelation is indicated by a cyclical pattern that is something that swings and doesn't cross the x-axis very often. That would indicate positive autocorrelation. What about negative autocorrelation? Well, negative autocorrelation is exactly the opposite phenomenon. That would be where one residual is negatively related to its immediately preceding or next value. So on average, in the presence of negative autocorrelation, if the residual at time t minus 1 is positive, the residual at time t will be negative. If the residual at time t minus 1 is negative, the residual at time t will be positive most of the time. If we plot the residuals at time t on the y-axis against the residuals at time t minus 1 on the x-axis, negative autocorrelation would be represented by the majority of the points being in the top left of the diagram or in the bottom right of the diagram. If we plotted the residuals over time, a negative autocorrelation would be indicated by a pattern where the residuals cross the x-axis very, very frequently. So in the diagram that I've shown here, we've got points crossing the x-axis every time period. So if one residual is positive, the next one's negative. If one is negative, the next one's positive, and so on. So we could say negative autocorrelation is represented by an alternating pattern where the residuals cross the time axis more frequently than they would if they were distributed purely randomly. So that's positive autocorrelation and negative autocorrelation. What's the final pattern? Well, the final pattern is one where there's no pattern. So if there were no autocorrelation in the residuals, what would that look like? Well, if we plotted the residuals on the y-axis against the values they took in the previous period on the x-axis, no autocorrelation would be indicated by a kind of random scattering of points in all four quadrants of that diagram. Similarly, if we plotted the residuals over time, no autocorrelation would be the case if the residual plot crossed the time axis neither too frequently nor too infrequently, but just the right number of times. So this would be the case where there were no discernible pattern in the residuals at all. And obviously, because we want the residuals to be autocorrelation free, this is the pattern that we want to see. So how do we detect autocorrelation in practice? Well, the first thing we could do again is to conduct a residual plot. We could construct the diagrams that I've put on the previous slides and examine whether the residuals from our estimated model seem to fit into any of those patterns. Now, unfortunately, that's unlikely to reveal anything in practice, because even if there were autocorrelation in the data, plots of that kind usually are very, very hard to interpret. Our regression model might have 50 or 100 or even 2,000 observations. And if we were to plot our 2,000 residuals coming from that model on a time series diagram, then we would just see lots and lots of points wobbling all over the place, and we probably wouldn't be able to see anything. So once again, what we actually need in order to be able to tell whether the residuals from our estimated model are autocorrelated or not is a statistical procedure. the simplest and most commonly used statistical procedure is known as the Durbin-Watson test. Now, the Durbin-Watson test is a test for first-order autocorrelation. That is, it's a test for whether the residual at time t is related to its value at time t minus 1. It's not a test for whether the residual at time t is related to its value at time t minus 2, t minus 3, and so on. So it's only a test for first-order autocorrelation. Now, the Durbin-Watson test works as if, for the population regression function, we were to take a disturbance and regress it on its previous value and calculate the value of that slope coefficient. Now, in this equation, which I've called 1, notice that we don't need to have an intercept because by assumption the expected or average value of the disturbances is 0. So we don't need to have a disturbance in the regression to allow them to have a non-zero mean because by assumption they have a 0 mean. So the Durbin-Watson test works as if we've run this regression and calculated the value of rho, which will be the correlation between the disturbance at time t and the disturbance at time t minus 1. Vt in this regression equation 1 would simply be another disturbance term whose properties we assume are identical to the ones that we assumed usually for regression models. So the Durbin-Watson test actually tests the null hypothesis that the true value of rho is 0 in that equation 1 against a two-sided alternative that it's not 0. Now it turns out that although the Durbin-Watson test works as if we'd estimated this regression equation 1, we don't actually need to estimate any regression equation on the residuals in order to be able to calculate the value of the Durbin-Watson statistic. In fact, if you look at the formulation of the Durbin-Watson statistic, you can see that it only incorporates the values of the residuals at time t and time t minus 1 and nothing else. So we can calculate the value of the Durbin-Watson statistic using only information that we can obtain from the first regression that we estimate. We don't need to estimate an auxiliary regression to conduct a Durbin-Watson test. What does the Durbin-Watson test statistic look like? Well, in the numerator of the expression, we've got the sum of the squares of the differences between the residuals at time t and time t minus 1. And we kind of normalise or scale or divide by the sum of the squared residuals. Notice that in both of these sigma or summation signs, the sum starts from lowercase t equals 2 rather than t equals 1. The reason that the sums start from 2 rather than 1 is that when we construct the Durbin-Watson statistic, obviously it includes a lagged value of the residual, i.e. it includes u hat t minus 1, and we lose one observation when we compute that lag. So how does the Durbin-Watson statistic work? Well, if you look at the numerator, it measures the sum of the squares of the distances between one residual and the immediately previous one. And that's the most important part of the formula. If you think about what this actually means, well, in the presence of positive autocorrelation, because if one residual is positive on average, the next one is positive. If one is negative on average, the next one is negative. That means in the presence of positive autocorrelation, most of the time the distance between one residual and the immediately previous one will be relatively small. So positive autocorrelation will lead to a small value of the Durbin-Watson test statistic. On the other hand, negative autocorrelation means that the residuals are changing sign very frequently. That means that if one residual is positive, typically the next one will be negative, then the next one will be positive, and the next one negative, and so on and so on. So we've got distances between one residual and the previous one being relatively large. So for negative autocorrelation, the Durbin-Watson statistic will take on a relatively large value. For no autocorrelation, the Durbin-Watson statistic will take on a value that's between this small value and large value that would correspond to positive and negative autocorrelation respectively. Now it turns out that we can be a bit more precise than that in our interpretation of the Durbin-Watson statistic. And we could derive some algebra, and I do this in my book, we could derive some algebra which shows that the Durbin-Watson statistic is approximately equal to 2 multiplied by 1 minus the estimated correlation coefficient between u hat t and u hat t minus 1. Now, if rho hat is an estimated correlation coefficient, then obviously its value must lie between minus 1 and 1. So let's just think for a minute about what each of these two values means for the value of the Durbin-Watson statistic. So first of all, I said that we could define rho hat as being the estimated correlation between u hat t and u hat t minus 1. Okay, so given that rho is a correlation, we know that rho hat must take on values between minus 1 and 1. And the value of rho hat of 0 obviously implies no autocorrelation, or no correlation between u hat and u hat t minus 1. So that's an interesting value to look at as well. We can then say, well, for given these values for rho, and given that there's an approximate relationship that holds between rho hat and the Durbin-Watson statistic, we could say, what are the values of the Durbin-Watson statistic that correspond to this value of rho hat? Well, first of all, what is the value of the Durbin-Watson statistic if rho hat takes on a value of minus 1? Well, if we plug minus 1 into this formula, we've got 2 multiplied by 1 minus minus 1, which is 2 times 2, which is obviously 4. So if rho hat is minus 1, Durbin-Watson statistic is approximately plus 4. What happens if rho hat is 0? If rho hat is 0, Durbin-Watson equals 2 multiplied by 1 minus 0, and 2 multiplied by 1 minus 0 is obviously 2. So if rho is 0, Durbin-Watson is 2. What about if rho equals 1? Well, Durbin-Watson is then approximately equal to 2 multiplied by 1 minus 1, which is 2 times 0, which is obviously 0. So we can say immediately that Durbin-Watson must lie between 0 and 4. Okay? A Durbin-Watson value close to 4 indicates negative autocorrelation. Okay? A Durbin-Watson value of 0, a Durbin-Watson statistic close to 2, on the other hand, indicates no autocorrelation. A Durbin-Watson statistic value of 0, on the other hand, indicates positive autocorrelation. So these are the possible values that the Durbin-Watson statistic could take on, and their interpretation. So now we're armed with those, we can think a bit more about how we actually use the Durbin-Watson statistic in practice. Now, what we do is to calculate the Durbin-Watson statistic using that formula, while in fact the computer will do all of that for you, so it will calculate the value of the statistic and it will automatically tell you that. We then need to compare the value of this test statistic with a critical value from a distribution. Now, several things are unfortunate about the Durbin-Watson statistic. The first is, you can see immediately that because the Durbin-Watson statistic lies between 0 and 4, it can't follow any standard statistical distribution. So you can see that if something is bounded to be between 0 and 4, we couldn't say it follows a t distribution or an f distribution or a normal distribution or a chi-squared and so on. So in fact, the Durbin-Watson statistic follows a non-standard distribution. That means that in order to calculate critical values for that distribution, one would need to conduct a simulation study. So the critical values from the Durbin-Watson distribution, if you like, that we get from statistical tables have been derived from simulation studies rather than from analytical formulae. A further unfortunate point about the Durbin-Watson test is that it has both a lower critical value, which we denote by d subscript L, and an upper critical value, which we denote by d subscript U. And also, there is 2 intermediate regions where we can neither reject nor not reject the null hypothesis when we use the Durbin-Watson statistic. So let's have a quick look at an example. And let's suppose that we calculate the value of the Durbin-Watson statistic And it turns out that it takes a value of 0.86. So let's say that we've applied the formula that I put on the PowerPoint slide previously, and the value of that Durbin-Watson statistic is 0.86. Let's suppose also that the regression model that we actually estimated was as follows. So let's suppose that the original regression model that we wanted to test was of the form yt equals beta 1 plus beta 2 x2t plus beta 3 x3t plus beta 4 x4t plus ut. Okay? So in the notation that I've used previously, k, the number of parameters to be estimated here, would be obviously equal to 4. Okay, so let's suppose that the Durbin-Watson statistic took on a value of 0.86, and let's also assume that we had t equals 80 observations at our disposal to estimate the regression model. How would we perform the test? Well, we've got the value of the test statistic. We now need to look in the Durbin-Watson tables. If we look in the Durbin-Watson tables that you've been provided with, we'll see that the first column gives us the number of observations, t. So we can see that the number of observations, t, given in the tables ranges from 15 up to 100. Now, an obviously unfortunate circumstance is that if we had a regression model that was estimated using more than 100 observations, we wouldn't be able to find a critical value from the table. We'd then be faced with two possibilities. One would be that we could go away and conduct our own simulation study and fill in the rest of the table for numbers of observations bigger than 100. Or as another possibility, we could just use the value t equals 100 and assume that that also applies for larger numbers of observations. If we look in the last few rows of the Durbin-Watson tables, we can also see anyway that the values of the critical values are not changing very much as we increase the number of observations once we get to 100. But in this example, I've said that we've only got 80 observations anyway. Now you'll see, if you look in the headers to the columns for the Durbin-Watson statistic, there's something called k prime or k dashed. What is k prime or k dashed? Well, the answer, k prime is equal to the number of explanatory variables in our regression model, not including a constant, or the number of parameters we're estimating on the slopes and not including the intercept. So that's obviously going to be equal to what I called k minus 1, which in this case is obviously 3. So we need to look in the two rows marked k prime equals 3, and that will give us the values of the Durbin-Watson test that we need. So we've got a column marked DL, and we look in k prime equals 3 and row t equals 80 observations, and DL, the lower critical value, will be 1.56. DU, the upper critical value for that test, turns out to be 1.72. So we've got a test statistic value of 0.86, we've got a lower critical value of 1.56 and an upper critical value of 1.72. What does that tell us about whether we should reject or not reject the null hypothesis of no first order autocorrelation? Well, in order to answer that, we need to have a look again at the values that the Durbin-Watson statistic takes. And we could plot the values that the Durbin-Watson statistic can take on a number line running from 0 to 4. So if the Durbin-Watson statistic takes on a value between 0 and the lower critical value, then we'd reject the null hypothesis and conclude that we had evidence of positive autocorrelation. If the Durbin-Watson statistic lies between 4 minus the lower limit and 4, then we reject the null hypothesis of no autocorrelation and say that we'd found evidence of negative autocorrelation. If the Durbin-Watson statistic lies between the upper critical value and 4 minus the upper critical value, that is, it's relatively close to 2, then our conclusion would be that we did not reject the null hypothesis. So we got no evidence of autocorrelation. Finally, if the Durbin-Watson statistic lies between the lower critical value and the upper critical value, or between 4 minus the upper critical value and 4 minus the lower critical value, then those would be the inconclusive or indeterminate regions where we could neither reject nor not reject the null hypothesis. So once again, if the test statistic falls in this inconclusive region, that doesn't mean that we don't reject the null hypothesis. Instead, it means that we can't decide whether we reject or not reject the null hypothesis. In other words, in that context, the conclusion would be that there is no conclusion. We'd have to use some other approach to tell whether we got autocorrelation or not. Now, if we look down the columns of the Durbin-Watson critical value tables, we'll see that as the number of observations increase, and therefore the number of degrees of freedom increases, the lower and upper critical values get closer and closer together, and therefore the sizes of the inconclusive or intermediate regions is gradually reduced. So that being the case, the size of the inconclusive regions is reducing as the number of observations increases. That's what we'd expect. So if we've got 80 or 100 or 200 observations, the chances of us reaching an inconclusive conclusion is actually quite small. So going back to the circumstance we've got here, test statistic value 0.86, lower critical value 1.56, we can see clearly that we end up in the extreme left-hand part of this number line, and our conclusion is that we have positive autocorrelation. Now, it turns out that in practice, if we're estimating regression models with financial or economic time series data, then this is the most likely circumstance to happen. That is, in practice, we're much more likely to observe positive autocorrelation than we are to observe negative autocorrelation. Now, unfortunately as well, another problem with the Durbin-Watson statistic is that there are 3 conditions which must be fulfilled for the Durbin-Watson test to be a valid approach. The first of these is that there must be an intercept or constant term in the regression model. So even if financial or economic theory suggested that the regression model must go through the origin, then in that situation we could not validly use the Durbin-Watson test. Secondly, and this was one of the assumptions of the classical linear regression model, we assume that the regressors are non-stochastic. This assumption is also required for the Durbin-Watson test. Finally, and this would be an example in fact of the second of these, and the final condition that must be fulfilled for Durbin-Watson to be valid is that there must be no lags of the dependent variable in the regression model. Why would we include lags of the dependent variable in the regression model? We'll come to that idea a bit later on. But all we need to know for now is that there are a set of circumstances within which Durbin-Watson will be valid. For other circumstances and other regression models, we can't use the Durbin-Watson test. We need to use some other approach. The other problem with the Durbin-Watson test is that it's only a test for first-order autocorrelation. What does that mean? Well, that means there could be some forms of autocorrelation that are present in the residuals from our estimated model, but which the Durbin-Watson approach couldn't actually find. So, for example, suppose that the correlation between u hat t and u hat t minus 1 was quite small, close to 0. Let's say 0.02. So here we can see we've got very little evidence of first-order autocorrelation. But let's suppose that the correlation between u hat t and u hat t minus 2 was some very high value, let's say 0.85. Now, if we use the Durbin-Watson approach, the Durbin-Watson test would only focus on this, and therefore it might suggest that our regression model residuals were free from autocorrelation. But if we looked at the second-order autocorrelation here, we'd see that that was very high. So if this were the case, clearly we will have violated the assumption that the disturbances are statistically independent of one another, but this wouldn't be in a way that would be picked up by the Durbin-Watson approach. So what we need is some other approach to testing for autocorrelation, which first of all can apply in a wider set of circumstances than Durbin-Watson, and secondly that allows us to pick up the possibility of higher orders of autocorrelation in the residuals than Durbin-Watson does. One such approach is, and there are many of these approaches actually, but one such approach, which is programmed up in many computer packages including eViews, is known as the Breusch-Godfrey test. Now the Breusch-Godfrey test is a more general test for autocorrelation of up to rth order. So we can test for the correlation between u hat t and u hat t minus 1, between u hat t and u hat t minus 2, and so on, up to the correlation between u hat t and u hat t minus r, where r is some integer value that we choose. So under the population regression function, essentially the test is one of the joint significance of the values of the coefficients ρ in this model against a two-sided alternative where they're not zero. So how do we conduct the Breusch-Godfrey test in practice? Well, once again, as with the White test for autocorrelation, the first step is to estimate the regression model that we wanted to test using ordinary least squares and to calculate the residuals. Once we've collected those residuals, we regress the residuals on all of the regressors from the first stage, that is the explanatory variables, plus all of these lagged values of the residuals that we want to test. Why do we need to regress u hat t on the original explanatory variables as well as the u hat lags? Well, I don't want to go into that in any great detail, but suffice to say for now that we need to include those original regressors in the auxiliary regression just to ensure that the test statistic follows the distribution that we say it does. So we regress u hat t on the original explanatory variables, the regressors, plus the lagged residuals, R lagged residuals. Once again, we could use two approaches to testing this. We could use the F-test approach, where we would run the unrestricted regression, which would be this regression that I've just stated under point 2. We would then run a restricted regression, which would be just a regression of u hat t on the original explanatory variables, and we could calculate the residual sums of squares for those two and statistically compare between them and compute the value of the F-test statistic in the usual way, or we could use this Lagrange multiplier test that I mentioned earlier. That is, what we could do is run this auxiliary regression of u hat t on the explanatory variables and the lagged residuals, and we could obtain r squared from that regression and multiply it by the number of observations. Now, how many observations would we have for this auxiliary regression? Well, if our original sample had capital T observations in it, when we estimate the auxiliary regression, obviously we've calculated R values of the residuals to use as regressors in the auxiliary regression. So therefore we've lost the first R observations from the sample. So the value of this test statistic would be R squared from the auxiliary regression multiplied by T minus R, which is the effective number of observations that we've got in the auxiliary regression. This test statistic would again follow a chi-square distribution with degrees of freedom equal to the number of restrictions that we're testing. How many restrictions are we testing? Well, we're testing the restriction that all R lagged values of the residuals have no explanatory power for the current residual. So the test statistic follows a chi-square distribution with R degrees of freedom. Once again, if the test statistic exceeds the chi-squared critical values from the statistical tables, we'd reject the null hypothesis of no autocorrelation. If, on the other hand, the test statistic was smaller than the critical value from the statistical tables, we would not reject the null hypothesis, and we conclude that we had no significant evidence of autocorrelation. An obvious question to ask, therefore, is what is the appropriate value of R, that is the number of lags of the residuals, to include in the auxiliary regression? Now, unfortunately, there's no single scientific answer to that question, so we have a number of approaches that we could use. The first approach is to say what we should do is to use a range of values of R and then examine whether the conclusions from the test are altered by using a different value of R. So, for example, we could use R equals 1, R equals 2, R equals 3, and so on, up to R equals 10. And hopefully we get the same conclusion in every case. That is, we would either reject the null hypothesis and find autocorrelation in every case, or we would not reject the null hypothesis and not find autocorrelation in every case. The other approach that we could use is to what people call letting the frequency of the data decide the appropriate value of R. So in that circumstance, if we got daily observations, for example, in our regression model, then we might say there are 5 days of the week. So we'd use R equals 5, and then we'd let the 5 lagged residuals corresponding to the last 5 days possibly affect the current value of the residual in our test. For monthly data, we've got 12 months in the year, so we might let R equals 12, and then we'd have the last 12 lagged residuals being allowed to affect the current value. If we got quarterly data, we might use R equals 4 and so on. So you can see that this isn't a very scientific method to calculate the value of R, but instead we've got a number of ad hoc approaches that we can use. Hopefully, whatever value of R we use, we'll always get the same conclusions.